This screencast will cover factorial ANOVAs. In this screencast, you will learn how to carry out and interpret a factorial ANOVA test, how to examine significant main effects in factorial ANOVA, how to follow up a significant interaction effect in factorial ANOVA using the syntax window, and how to report the result of a factorial ANOVA test. Suppose you are asked to examine sit and reach flexibility scores in a sample of males and females from 3 different age groups, 20 to 29 years, 30 to 39 years, 40 to 49 years. The purpose is to examine whether there are age group and sex differences in flexibility. You have 2 independent variables, age, which has 3 levels, 20 to 29 years, 30 to 39 years, and 40 to 49 years, and sex, which has 2 levels, male and female. You also have 1 dependent variable, flexibility. Your SPSS data file has each of your variables listed, flexibility, age group, and sex. We have 2 independent variables, age group and sex. We are interested to examine whether sex differences in flexibility are more salient for some age groups than others. In other words, we want to examine whether there is a significant interaction between the variables age group and sex. The assumptions of a factorial ANOVA are identical to those of a one-way ANOVA. Please refer to the screencast on one-way ANOVAs for assumptions. To begin the analysis, click Analyze. Click General Linear Model. Click Univariate. This will open up a new window called Univariate. You can see each of your variables listed on the left-hand side. Click Age Group, and then click the arrow to the left of the box labeled Fixed Factors. This will move Age Group into the Fixed Factors box. Click Sex, and click the same arrow as you did before to the left of the Fixed Factors box. This will move your second independent variable, sex, into the Fixed Factors box. Click your dependent variable, flexibility, and click the arrow to the left of dependent variable box. This will move flexibility into the dependent variable box. Click Plots. This will open up a new window called Univariate Profile Plots. This window will help us tell SPSS to create a plot for our output. Plots can produce a graph showing the interaction between age group and sex, which can be very useful when you try to make sense of the interaction, if the interaction is significant, of course. When producing interaction plots, it makes more sense to move the independent variable with the fewer levels in the separate lines box, and the independent variable with more levels in the horizontal axis box. So click on Age Group and click the arrow to the left of horizontal axis, and that will move it across to the horizontal axis box. Click on Sex, your second independent variable, and click the arrow to the left of Separate Lines. This will move sex into the Separate Lines box. You must then click Add, and this will add your plot to the Plots box. If you do not click Add, your plots will not display in the output. Click Continue. Click Post Hoc. This will open up a new window called Univariate Post Hoc Multiple Comparisons for Observed Means. In this window, you will have a post hoc run for age group. Since sex only has 2 levels, we cannot request post hocs for this independent variable. Click on Age Group, and then click to the arrow between Factors and Post Hoc Tests for. Click on Tukey, located underneath the heading Equal Variances Assumed. Click Continue. Click Options. This will open up a new box called Univariate Options. Similar to a one-way ANOVA, you will click Descriptive Statistics, Estimates of Effect Size, Observed Power, and Homogeneity Tests, then click Continue. This now takes you back to your univariate window. To have SPSS run the Factorial ANOVA, click OK. As you can see in the area outlined in yellow, it displays the descriptive statistics for your data. You can see each of the age groups and each of the males and females. For example, if we focus on the box that says 20 to 29-year-olds, we see that the mean for males is 30 and the mean for females is 32.9. We also see the total, which is the total for all 20 to 29-year-olds. That means it takes into account both males and female score, and that mean is 31.45. If we look at the means displayed in this output, we could determine if there may be something going on. That means if there are something different between males and females across age. The decline in flexibility from the second to the third age group is much steeper for males than females. This indicates that the interaction is possibly significant. However, we do not know if the interaction is significant or not until we look at the statistics later in the output. The box currently outlined in yellow displays Levene's test for equality of variances. The results here are not significant, therefore the homogeneity of variance assumptions are met in this data set. If the Levene's test was statistically significant, meaning the assumption was violated, there are a couple of options. Unfortunately, unlike one-way ANOVA, there is no widely accepted non-parametric equivalent for Factorial ANOVA. However, similar to one-way ANOVA, Factorial ANOVA is robust to moderate violations of this assumption. A second option would be to repeat the analysis and choose a post hoc test. That is more appropriate when the assumption has been violated, for example, the Games Hall test. The current area, outlined in yellow, is the tests of between subjects' effects. This is similar to the table interpreted in the one-way ANOVA. The main difference is that this table contains an F value for each of the main effects, each of your independent variables, and an F value for the interaction. The current box, highlighted in yellow and outlined in blue, shows the main effect for age group. It tells us that there is a significant overall main effect for age group. The F value is 20.775, and the significance value, or the p-value, is less than 0.05. This tells us that the means of the three age groups are significantly different. The box now highlighted in yellow refers to sex. It is saying, is there a significant difference between males and females? The F value is 50.200, and the significance value, or your p-value, is less than 0.001. That means there is a significant main effect for sex. The current box highlighted in yellow is the interaction, so the interaction between age group and sex. The F value is 3.306, and the significance value, or the p-value, is 0.044. This means there is a significant interaction between age group and sex. This means that sex differences in flexibility are more pronounced for some age groups than others. Alternatively, it can be interpreted the opposite way. age group differences in flexibility are more pronounced in one sex group compared to the other group. Since the interaction is significant, the main effects for sex and age group should not be interpreted, because they are meaningless. However, for the purpose of the screencast, let's pretend that the interaction was not significant, and go over what to do. We therefore need to interpret the main effects. Let's start with age group. The multiple comparisons table presents the results of the Tukey's post hoc test. As you can see here, the multiple comparisons box is outlined in yellow. This output tells us that there are significant differences between the two younger groups, the 20 to 29-year-olds and the 30 to 39-year-olds, compared with the oldest group, the 40 to 49-year-olds. P is less than 0.05. There are no significant differences between the 20 to 29-year-olds and the 30 to 39-year-olds because P is 0.41, which is greater than 0.05. A post hoc was not run for sex because the variable only has 2 levels. We can evaluate the mean scores for males and females collapsed across all age groups in the descriptive statistics box found at the beginning of the output. If we look here, we can see that females had higher flexibility scores than male, with 31.73 being their mean, compared with males' 27.90. Now we are going to look at the interaction plot, which would be your first step if the interaction was significant. The interaction plot is very useful. It shows us that flexibility declines with age in both sex groups. However, the decline from the second to the third age group is much steeper for males than females. We could write up our results using the interaction plot provided in the output. However, it is also interesting to carry out follow-up pairwise comparisons, called tests of simple effects, to disentangle the nature of the interaction. In theory, a number of research questions can be answered here. For example, our first question could be, is the decline in the male scores between the 20 to 29 age group and the 40 to 49 age group significant? Our second follow-up question could be, is the difference in flexibility between males and females in the 40 to 49 age group statistically significant? Unfortunately, the answers to these and many other interesting questions are not provided by the standard SPSS output, so we have to follow a relatively lengthy procedure to obtain them. Click Analyze, and then click General Linear Model. Click Univariate. Then click Paste. By clicking the Paste button, we will paste onto a syntax, the SPS command for univariate. We are going to edit the SPSS command between the line that says \plot and \print. I have highlighted the area where I have typed the code in. It does not appear highlighted in SPSS. The highlighting is so you can see what to type in. You type this in between the plot and the print lines of the SPSS syntax. The commands we have typed in do 2 things. The first subcommand will compare the age groups separately for males and females. This subcommand can answer questions related to age declines and flexibility separately for each group. The second subcommand will compare sex differences separately for each age group. This subcommand can answer questions related to sex differences and flexibility separately for each group. To retain the experimenter-wise error at 0.05, all these comparisons will be adjusted using a method called Bonferroni. Obviously, with a different dataset, you will need to change the names of the factors, age group and sex, in the command, but everything else will be kept the same. We are now going to run the syntax. To do this, highlight your univariate outline in the syntax completely and click the play button, which is the green triangle located near the top of the page. About halfway down the output, you will now see a box called Pairwise Comparisons. This is the product of the first subcommand. This can help us answer the question, is the decline in the male scores between the 20 to 29-year-old age group and the 40 to 49-year-old age group significant? As you can see here, yes, it is, because p is less than 0.05. The current table outlined in yellow, univariate tests, examine whether there is an overall significant trend in the changes of flexibility scores across age, separately for males and females. In some respects, the information in this table is similar to two separate one-way ANOVA tests, one for each sex group. The results indicate that the decline in flexibility across age group was significant for both males and females. A little bit further down, you will see another table called pairwise comparisons. This is the product of the second subcommand we added. This answers our question of, are there differences between males and females at 40 to 49 years old? As we can see here, in the area highlighted in yellow and outlined in blue, there is a significant difference between males and females at 40 to 49 years old. This is because the p-value is less than 0.05. The table below the pairwise comparisons, called univariate tests, tells us that there is a statistically significant difference between males and females at each of the age groups, because the p-value for each of the age groups is less than 0.05. When reporting the results of a factorial ANOVA test in text, you should present separately for each main effect and the interaction. As you can see here, we report the results for both sex and age, and the results for the sex and age interaction. Since the interaction was statistically significant, we use the plot below to describe the interaction. You can also present a table with the mean score for each of the conditions, as you can see here on this slide. For complex factorial designs with many independent variables and interactions, you can present a separate table with all f values, their degrees of freedom, and their p-values. This concludes the screencast on factorial ANOVAs. In this screencast, you learned how to carry out and interpret a factorial ANOVA test, how to examine significant main effects in factorial ANOVA, how to follow up a significant interaction effect in factorial ANOVA using the syntax window, and how to report the results of a factorial ANOVA test.